Okay, so having learned the product rule and the quotient rule, now we can go into an additional class of functions, right? So if you have a function x to the negative n, okay, where n is a positive integer, so now the exponent is negative, okay? So this is actually the same thing as 1 over n, right? Do we know how to differentiate this? We had the power rule, which applies when the exponent is positive. But if, oh, by the way, you know, if this is the case, differentiating this will give you 2x, right? If x1 is there, then of course that would give you 1 times x to the 0th, and of course that's just 1, you know, assuming x is not 0. So that's fine too. But what happens if x to the 0th power? Well, that's equal to 1. So that just becomes 0. Okay, so that's not a problem if the exponent happens to be 0. And we can handle all these positive integer exponents. Now we are talking about negative exponents, negative integer exponent. Okay, can you differentiate this? Well, now we have the quotient rule. Wow, we do. Yes, so we can do that. Right? Let's take the derivative of this. What is the derivative of this? Remember, the denominator becomes squared. Maybe you can identify this as your f of x and this as your g of x. Okay, so the first one on the numerator is the derivative of f, which is, I mean, I'm sorry, I should, well, we have two f's involved in here. But the derivative of the top is 0, okay? And that's followed by g of x, which is x to the n, minus, maybe I should say, by the quotient rule, the derivative should be 0 times x to the n minus the derivative of g, which is n x n minus 1, times the f without differentiating, right? Remember, it's f prime g minus g prime f, and the denominator is that. So what happens is this is a negative n, x to the negative 1, all over x to the 2n. Let's simplify this. It's minus n, and how many x's do I have here? It's going to be x to the n minus 1 minus 2n, right? Because that's how the exponents work. When you have a quotient, you subtract the exponents. Well, how many x's are there here? N minus 2n is negative n. So it's negative n minus 1. So look, this is exactly what we did before. You started with the exponent, right? We moved this to the front and subtracted 1 from it. That's exactly what we did this time too. You took the exponent, moved it to the front as the coefficient, and the new exponent is 1 less than negative n, or the original exponent. So that's nice. Okay, so this is actually called the extended power rule, which is exactly what I just said here, but you can even combine this with the first power rule we learned. And that one basically says the derivative of x to the n is n times x to the n minus 1 for all integers n. Okay, and by the way, if n is equal to 0, this is what happens, right? And because n is equal to 0, that is also 0, and so this works as well. All right, a few examples will probably help. The derivative of 1 over x, which is x to the minus 1. What do you think this is? Well, you move that exponent to the front, and then x to the negative 2. Okay, so this is 1 over, negative 1 over x squared. Okay, we actually saw this some time ago, a few sections ago. All right, if somebody says differentiate 1 over x to the 13th. What do you get? Okay, now you can of course identify this as x to the negative 13. So the derivative is going to be negative 13 times x to the negative 14th. Remember, you subtract 1. Here, the original exponent over here was negative n, and you subtract 1 from it. And that's what you do, right? So you can also, of course, write this as negative 13 over x to the 14th power. If you write this in the denominator, of course, you don't have the negative exponent. So that is how you work these problems out. So now we know the power rule applies to all integer exponents, not just positive integers. All right, I will close this section with one application, which is again foreshadowing something extremely, extremely important and powerful. One of the reasons you are learning calculus as a science student, or maybe even as a business student or a social science student, whatever, maybe because of this application, right? Many times we want to find when a function as a model is achieves its maximum or minimum, because you want to optimize something. And just this much knowledge here so far is going to help you address those problems, okay? So let's say you have this function, and actually here, let me go ahead and do this. Okay. Now this function, the graph that I have just drawn, resembles the graph of x cubed minus 7x squared plus 8x plus 1. Okay, this is my function. Find where the tangent line, you'll see what I'm talking about in a minute, find where the tangent line is horizontal. Okay, now we have never directly answered this kind of question. So what are we talking about? Remember, the tangent line being horizontal means the slope of the tangent line has to be equal to 0, which means the derivative has to be equal to 0. So all you have to do to solve this question is to find where the derivative is equal to 0. Let's find the derivative. 3x squared minus 14x plus 8. Man, how do we do this so quickly? Do I take the limit as h approaches 0? Of course not. All I did was to differentiate each of these term by term, because this happens to be a polynomial function. What happens to this one? It disappeared because the constant goes away when you differentiate it. 8x became 8, right? So again, term by term, you simply differentiate this in 1 second, maybe 2. All right. So you want this set this equal to 0, because that means that the horizontal tangent means that the derivative is equal to 0. So set f prime equal to 0, because we are looking for a horizontal tangent. Do you know how to solve this? Well, it's a quadratic formula, because you started with a 3rd degree, and then when you differentiate a polynomial, basically the degree goes down by 1, simply because of the power rule. All right, take a look at this. Do you know how to solve this? Maybe you can use a quadratic formula. Maybe, but I think maybe you can do this by factoring. Can you? I don't know. To have 3 in the front, you have to have 3x and x. For 8, you can have 2 and 4, or 1 and 8. I think 2 and 4 would work, because 2 in here, 4 here. The outer product is 16, inner product is 2. I bet I can create a negative 14 by doing this, right? So now it's 3x squared, old FOIL, right? Negative 12x plus 2x. No, that's not true. Negative 2x minus 12x is negative 14x. And then negative 2 times negative 4 is positive 8. Cool. All right, so that means one of these is equal to 0. Remember the 0 property of the reals. That means if a, b is equal to 0, one of those a and b must be equal to 0. So x is either 2/3 or 4. Now, this graph shows you where that is. This has to be 2/3, and this has to be 4. How do I know this? Because this is where the tangent looks horizontal, right? And what do we just find? When the tangent is horizontal, when the derivative is equal to 0, means you have found these, places where the f is highest in this region locally, and the f is lowest here. This is actually called the absolute. Sorry. This part is called a relative or local maximum, and this point is called the local minimum. All right, and so these will help us as we look for maximum and minimum points of a function. Again, this is one of the most important applications of differential calculus, and we are already seeing that important role of calculus as we start chapter 3. Okay, so that's all I have to say about section 3.3, and now it is time for you to practice by doing your exercises, doing your assignment, and master these concepts. 3.3 has a lot of content, so make sure you learn how to differentiate various functions using all of these rules. All right, have a wonderful day and enjoy calculus.